Okay, let's look at number 8. It says the rabbit population at the city park increases by 10% each year. In 1990, there were 240 rabbits. Use an exponential model to represent the growth rate of rabbits since 1990. Okay, so we know that an exponential model has the form, if I want to, oh, sorry, I forgot to pick up my pen. So if I want to represent a formula or create a formula for the growth for an exponential model, I'm going to use P sub n is equal to 1 plus r raised to the n times P sub 0. Alright, so in year 0, there were 240 rabbits. Year 0 is 1990. Let me make this a little bit better here. And year 0, which is 1990, there were 240 rabbits. So P sub 0 is equal to 240. I know that the rate R is 10%, so it's 0.10. So I can fill that in. And so in my formula, P sub n is going to be, I'm going to start out with P sub 0. So it's going to be 240. And you can put P sub 0 first if you want, since multiplication, you can switch these around. Times 1.10, that's the growth multiplier, raised to the n. Alright, now we want to find the rabbit population in 2007. So in 2007, that is 17 years. So 2007 is 17 years after $1990, right? And the way that I found that is I just took 2007 and subtracted 1990, and I got 17. So I'm going to try to find P sub 17. So that's going to be 240 times 110 raised to the 17th power. You can easily find that on the calculator. And when I find that on the calculator, I get 1,213 .07. So the rabbit population in 2007 is going to be approximately 1,213. Now, if you wanted, because of that 0.07, even though it's a very tiny amount, there's still going to be another, that's still going to represent another rabbit. You could say approximately 1214 as well. Either one would be okay, because remember, these are just estimates. Now this is this is an example really of extrapolation, because we only know for sure that in 1990 there were 240 rabbits, and the rabbit population increases by 10% each year. 2007 is way after 1990, so we're not sure if the population will continue with the same trend. All right, also, or not also, but now we have 9 and 10. So basically we're just going to use the calculator. We're going to put log 2.5 into the calculator. And when I do that, I get 0.39749. Oh, 794, sorry. And then when I put ln27 in the calculator, I get 3.29584. So as long as you have your calculator, you'll be able to do those two. All right. Let's look at the next one. It says, Danny's parents tell him on his 10th birthday that he will receive a monthly allowance. Each year the allowance amount will increase. Below is a table showing how much allowance Danny receives each year. Draw a graph representing the data and use it to determine if the growth is linear, exponential, or logistic. All right, so when Danny is 10, he gets $8. So when he's 10, he gets $8. That's probably about right here. When he's 12, he gets $16. When he's 14, he gets $24. It's a little bit below half there. When he's 16, he gets $32. And when he's 18, he gets $40. Now, if I draw or connect the dots, in fact, okay, let me do that a little bit better. Sorry. If I connect the dots, you can see clearly that those are in a line. This is linear growth. All right, let's look at number 12 then. It says the city's population is currently 40,000 and is growing by 1.5% each year. If this continues, how many years will the city's in how many years will the city's population reach 87,000? So we want to use exponential growth because it's growing by a certain percent. So I know that P sub 0 is 40,000. And so I can create the explicit formula. P sub n is equal to 40,000 times 1.15 up 1.015 raised to the n. Now, I need to find out what n is, okay? So this is going to be a little bit different. So I know that I want to find out what n is when P sub n is 87. So P sub n here is going to be 87,000. So I need to set up this equation. 87,000 is equal to 40,000 times 1.0015 n. So the first thing I'm going to do is I'm going to divide by 40,000 on both sides. So I'm going to get 1.015 n is equal to 2.715. Okay, now what I need to do is I need to take the log of both sides. So I'm going to take the log of both sides, and then I can move this in front of the log. So really what I have, and I'm going to come over here, really what I have is log of 2.715 is equal to n times log of 1.015. And then I'm going to divide by this log of 1.015. That should be a decimal point on both sides. So then n is going to equal, when I do that division, and you can do that on the calculator, 67.08. So you can say approximately in 67 years, or since that 08 actually represents another year, you can say in approximately 68 years. Alright, let's take a look at solving these equations. So the first thing I'm going to do here with this one is get rid of that 4 by dividing by 4 on both sides. That way I have 10x is equal to 0.0001. Now I'm going to take the log of both sides, and since the common log of 10, it cancels each other out, I'm left with x. And this is just log of 0.0001. You can find that on the calculator. It happens to be -4. This one's going to be even simpler. All I'm going to do is take the natural log of both sides, ln e cancels each other out, so I'm left with x, and that's equal to the natural log of 0.1, that's -2.30259.